Now let's continue with this initial value problem. So what we would do is this. We would type in dsolve and then dy equals t plus, and what we got now is sine y, okay, and then we have our initial condition is y at 0 is 1 and the independent variable still is t. So once we do that, it's taking a little while, let's see. What it says is that it cannot find an explicit solution. That means our analytical technique did not work. Okay, so what we would do now is that we shall go ahead and use a feature called ODE45. Let me write that for you here. Okay, so we are going to use now what is called ODE45 to obtain numerical approximation for the differential equations in which we cannot analytically find a solution. And we are attempting a solution because the existence and uniqueness theorem, if we apply it on this differential equation or this initial value problem, it does guarantee us a unique solution. So before we go for ODE45, what we have to do first is that we shall go ahead and define what you call an anonymous function. MATLAB calls it anonymous function, or it doesn't. You don't have to know the terminology anonymous function because it's not a standard function in MATLAB. So what we are doing is that we are just defining this as a function of x, y, and so what happens with this is that our function dy dt or dy, that just equals f. And if we look for ODE45, okay, and I pulled it here, from MATLAB's help feature. So what it tells me is that what would give us a solution. I'm just going to go ahead and enlarge it for you here. Okay, so it tells us that if we use ty and apply, see, this is the ODE function. What is the ODE function? Oh, I'm sorry, I took it away from you. That's this function f. So what we will do is this, that we shall type f here, and then we shall give a bunch of values of t. Sometimes if we are lazy, just by trial and error, or we can just go ahead and do some numerical calculations, or look at the form of the function to find appropriate t span, or a span of values of t, and then here what the value of y at 0 is. So let's go by that those instructions. Okay, so what we have here is this, that we shall just say that ty is ODE45, okay, and then I'm saying that our function defining the derivative is f, okay, and let's just take 0 to 5 as the values for t. All right, and then we have 1. All right, and let's see what it does. Okay, see, what it does was this. I was doing this, that I did not really pay attention on that. See, when I gave it this command, it just went ahead and computed a bunch of values or approximate values of f, and as I told you, mostly it uses the Rangekata approximation method. Okay, and one moment, just keeps on doing this. And here, so what we have to be careful with this in such cases is that we should we can just put this semicolon prompt here. Okay, I hope I'm saying it right, to suppress that output. Okay, so it has gotten this output, and we can use all these outputs to sketch a And now notice this, if I had just told it that, just written ODE45 command, what it would do is that it shall just go ahead and give me an approximate plot here of the solution by using the points to, just connect these dots here by using the points of evaluation. And if you want to hide the dots, you can simply, again, just define ty like this. Okay, and if you say plot ty, then it's not going to show you the dots, and you can go ahead and change the thickness and the axes and the color of the line the way we did before. All right.